Chapter 10, Module 2. In the first half of this module, we shall apply Mayer-Vietoris theorem to compute various homology groups of topological spaces. In the second half, we see one or two instances where homology groups help in solving purely topological questions. We begin with recapitulating a few terms. Previously, we have shown that if X is a singleton, that is X has a point small x only, then Hn(x) is equal to the infinite cyclic group Z when n is equal to 0 and trivial otherwise. We have also seen that homotopy equivalent topological spaces have the same homology groups in each dimension. The 0th homology group is the free abelian group whose rank is exactly the number of path components of X. So, if X is path connected, then H0x is Z. If X has the path components Yj, then for each n greater than equal to 0, Hn(x) is the direct sum of the homology groups of Hn Yj. We have established Mayer-Vietoris sequence that if X is a topological space and U V are open subsets of X, then we get a long exact sequence as shown here. Now, we find that the homology group of S1 is Z when n is equal to 0 or 1 and it is trivial otherwise. If I take 2 points P and Q from S1, then deleting those points from S1 respectively, we get the open sets U and V. And of course, X is equal to U union V. By stereographic projection, U and V both are homeomorphic to R, and so Hnu and Hnv both are trivial whenever we take n not equal to 0. Again, U intersection V is the disjoint union of two spaces P and Q, each of which is homeomorphic to R. So, the disjoint union P and Q has the 0th homology group equal to H0P direct sum H0Q, and that is equal to the direct sum of the infinite cyclic group Z with itself. Now, we apply Mayer-Vietoris sequence and put the informations that we have accumulated. Here we see that S1 is path connected, so it has only one path component. Therefore, H0x is Z, and for any n greater than 1, Hn(x) is sandwiched between the trivial groups, and therefore, all Hn(x) is equal to 0 when n is strictly greater than 1. So, the only non-trivial portion of the Mayer-Vietoris sequence is 0 goes to H1x, goes to Z direct sum Z via the map F1, Z direct sum Z to Z direct sum Z via the map F2, and Z direct sum Z to Z via the map F3, and then Z to 0. Now, since F3 is surjective, we may apply first isomorphism theorem and get that Z direct sum Z quotient with kernel of F3, that is isomorphic to Z, and so kernel of F3 is isomorphic to Z. By exactness of the sequence, image of F2 becomes Z, and by a similar argument, Z direct sum Z quotient with kernel of F2 is isomorphic to image of F2, and that is isomorphic to Z, and so kernel of F2 is equal to Z. Therefore, image of F1 is Z. Now, kernel of F1 being trivial, H1x is isomorphic to H1x by 0, that is the quotient group H1x by 0, and that is isomorphic to Z, and so Hn S1 is Z when n equal to 0 or 1 and 0 otherwise. In the next example, we take X as S2, the 2 sphere. Then Hn S2 is equal to Z if n equal to 0 or 2 and 0 otherwise. We wish to show this. So, we take 2 points P and Q from S2 and delete them from S2 to get the open sets U as S2 minus P and V as S2 minus Q, such that X is equal to U union V. By stereographic projection once again, we can see that U and V are homeomorphic to R2, and so for every n not equal to 0, the homology groups of U and V are trivial. Again, U intersection V is homeomorphic to R cross S1, which is homotopy equivalent to S1. Therefore, Hn S1 is trivial for all n not equal to 0 and 1 and Z otherwise. S2 being path connected, the 0th homology group of S2 is Z. Now, again we apply Mayer-Vietoris sequence and get the sequence in this form. Proceeding as in the previous example, H1x will be equal to 0, the trivial group, and H2x is isomorphic to Z. Consequently, Hn(S2) becomes the infinite cyclic group when n is equal to either 0 or 2 and trivial otherwise. Now, we may generalize this idea and prove inductively that for any m greater than equal to 1, Hn Sm is the infinite cyclic group Z when n is equal to 0 or m and 0 otherwise. In the introduction, we have mentioned that singular homology actually generalizes the concept of simplicial homology. Earlier, we have seen how to compute the simplicial homology groups of S2, but one can easily understand that computation of simplicial homology groups is practically impossible for Sm when M is taken very large. But in the last example, we have seen that it is very natural generalization of computation of HNS2 to HNSM in case of singular homology. Next, we see another example where we compute the singular homology group of figure of 8 space. Suppose X is a figure 8 space. That means it is S1 wedge S1. Now, HNX, we want to show that it is Z direct sum Z when n is equal to 1, it is Z when n equal to 0, and it is trivial in all other cases. Consider an open set U obtained by deleting any point from the left circle, and the point should not be a common point of both the circles. And we obtain another open set V by deleting a point from the right circle, and that point should be chosen from V in such a way that it should not be the common point of the circles. Clearly, X is union of U and V, and as described, U and V must be homotopy equivalent to S1, and U intersection V is homotopy equivalent to a point space P. So, HNV and HNU both are equal to Hn of S1, and therefore, it is Z for n equal to 0 and 1, and in any other case, that is n greater than 1, it should be trivial. Also, capital X is path connected, so it has only one path component. Therefore, the 0th homology group H0x is equal to Z. Now, we put all these information in Mayer-Vietoris sequence. So, we get HNS1 direct sum HNS1 to HNX to Hn minus 1 p etc. to H1p, which goes to H1 S1 direct sum H1 S1, which goes to H1x, and that goes to H0p to H0 S1 direct sum H0 S1, and that goes to H0x and finally to 0. So, this is an exact sequence. Clearly, we see that Hnx is equal to 0 whenever n is taken as any integer greater than 1. Therefore, the non-trivial portion of the sequence takes the following form. We denote the maps Z direct sum Z to H1x by F1, H1x to Z by F2, and Z to Z direct sum Z by F3, Z direct sum Z to Z by F4, and the final one as F5. From the exactness of the sequence, we now get that F4 is surjective. Now, since F4 is surjective, we apply first isomorphism theorem there to get Z direct sum Z quotient kernel of F4 is isomorphic to image of F4, that is Z, thereby kernel of F4 is Z. Image of F3 is equal to kernel of F4 by exactness, and therefore, image of F3 is equal to Z. Again, by first isomorphism theorem here, we get Z by kernel of F3 is isomorphic to image of F3, and that is Z, and that gives kernel of F3 is trivial. Now, when kernel of F3 is trivial, image of F2 is also trivial by exactness, and since image of F2 is trivial, F2 is the trivial homomorphism, the 0 homomorphism, and kernel of F2 becomes H1x, and hence image of F1 is equal to H1x. But F1 is injective, so image of F1 should be Z direct sum Z. Hence, H1x is Z direct sum Z. We shall now see how the idea of homology groups provides solution to the purely topological problems. In what follows, we shall apply the technique of transporting a topological problem to the algebraic setup, resolve it, and draw conclusions about the original problem. Now, we prove that if we take Sm and Sn, where m and n are not equal, then they cannot be homeomorphic. If possible, let us suppose that they are homeomorphic. That means, there exists a homeomorphism f from Sm to Sn when m is not equal to n. Now, since f is a homeomorphism, there exists a homeomorphism f inverse from Sn to Sm, and of course, f inverse being the inverse of f, we have f composed f inverse is identity on Sn, and f inverse composed f is identity on Sm. So, without loss of generality, we assume that n is not equal to 0. For if n is equal to 0, then we shall choose m to be not equal to 0, because of course, both cannot be equal to 0, as we already know that m is not equal to n. Now, we apply the functorial property of Hn, that is Hnf composed Hnf inverse is equal to identity on Hn_Sn. Since m is not equal to n and n is not equal to 0, Hn_Sm is equal to 0, and so we get the chain z to 0, we have the function Hn f inverse, and 0 to z we have the function Hnf. Hence, from this diagram we see that the identity homomorphism is factoring through the trivial group 0, and that is impossible. Therefore, Sm and Sn cannot be homeomorphic when m is not equal to n. In the next theorem, we prove a very well known result which is known as Brouwer's fixed point theorem. It says that every continuous map f from Dn to Dn has a fixed point. Earlier, using fundamental groups, we could establish the result for the case n equal to 2, but now we can show the result for any n. Suppose f is a function from Dn to Dn which is given to be continuous, and assume that it is not having any fixed point. That is, for every z taken from Dn, fz must be different from z. Now, we consider the ray 1 minus t fz plus tz for t greater than equal to 0, that starts from fz and passes through z. This ray will meet the boundary Sn minus 1 at some point, say gz. Then we get a continuous function g from Dn to Sn minus 1, which is given by z goes to gz such that gz is equal to z for all z belonging to Sn minus 1. Now, we consider the following diagram, that Sn minus 1 is included within Dn, that is the boundary of Dn. So, I is the inclusion map, and Dn to Sn minus 1 is the function g that we have already defined. Now, let us take the case when n is greater than 1. This sequence of continuous functions induces another sequence of homomorphisms between the respective n minus 1th homology groups. As Dn is convex, Hm Dn is equal to 0 for every m, that we have already proved earlier. So, we have the corresponding sequence inside groups and group homomorphisms, that is Hn minus 1 Sn minus 1 to Hn minus 1 Dn is the homomorphism Hni induced from I, and Hn minus 1 Dn to Hn minus 1 Sn minus 1, we have the homomorphism Hn minus 1 G induced from G. Now, we see that Hn minus 1 Sn minus 1 is isomorphic to Z. On the other hand, Hn minus 1 of Dn is trivial. So, this is a sequence of homomorphisms and groups, that is Z to 0, 0 to Z. Once again, the functorial property says that Hn minus 1 G composed Hn minus 1 I is equal to Hn minus 1 of G composed I, and that is Hn minus 1 of I Sn minus 1, that is the identity on Sn minus 1, and that has to be the identity on Hn minus 1, Sn minus 1. So, that means the identity map is factoring through the group 0, which is impossible. Hence, such a G cannot exist, and therefore, there must be some Z in Dn such that Fz is equal to Z. Now, let us take the case when n is equal to 1. For proving this part, we do not need the technique of algebraic topology. Topological methods are sufficient to establish this. In this case, D1 stands for the closed interval minus 1 1, and S0 stands for its boundary, that is the set consisting of 2 points minus 1 and 1. As D1 is connected, image of D1 under any continuous function should be connected. As G is a continuous function, under G, D1 is mapped to either singleton 1 or to the singleton minus 1, but it cannot be a surjective function. So, it cannot be the whole of S0. So, Gz equal to Z for every Z belonging to S0 cannot be satisfied, as this contradiction is arrived. We get that the result is true for the case n equal to 1. Before we conclude, we want to point out that Mayer-Vietoris sequence may not give precise collection of homology groups all the time. There are certain situations where it can be applied to get an estimate of the homology groups, but unfortunately only using Mayer-Vietoris theorem we may not get the precise collection of homology groups. For example, if we take a torus and want to find out the singular homology groups, then we can see that Mayer-Vietoris sequence will give an estimate of the homology groups, not the precise collection. With this, we end chapter 10, module 2.